In this lesson, we will continue with our study of trigonometric integrals. So first, evaluate the square root of sine x times cosine cubed x. So I think the goal here should be to let u equal sine of x. So take that cosine cubed and save a cosine. So we'll write it as root sine x times cosine squared x times cosine of x dx. And according to the Pythagorean identities, cosine squared x is 1 minus sine squared x. So we have the integral of root sine x times 1 minus sine squared x times cosine x dx. And if u is equal to sine, then du is just equal to cosine x dx. So this becomes the integral of root u times 1 minus u squared, du. And if I distribute that root u, I end up with u to the 1/2 minus u to the, no, we need this, you multiply root u times u squared, the exponents add. 2 plus 1/2 is 5/2. And now anti-differentiate. The antiderivative of u to the 1/2 is u to the 3/2 times 2/3 minus u to the 7/2 times 2/7 plus c. So this is 2/3 times sine of x to the 3/2 power minus 2/7 sine of x to the 7/2 power plus c. Now, one more way to write that, just one thing to note, is that sine of x to the 3/2 power is the same thing as the square root of sine cubed x, just in case you have to input it into WebAssign this way. And similarly, sine of x to the 7/2 power is the square root of sine x to the 7th. I would assume it takes both, but just in case. Next we have the integral of cosine to the 4th x. So because the power on cosine is even, and that's all there is, we have to use half-angle identities. So first, cosine to the 4th x is cosine squared x, the quantity squared. And the half-angle identity says that cosine squared x is equal to 1/2 times the quantity, 1 plus cosine of 2x, all squared. And now expand. So 1/2 squared is 1/4. The integral of 1 plus 2 cosine of 2x plus cosine squared of 2x. And on the cosine squared of 2x, you have to use the half-angle identity again. Instead of x, you're using it with 2x. So that gives us 1/4, the integral of 1 plus 2 cosine 2x plus 1/2 times 1 plus cosine of 2 times 2x, which is 4x. Distribute the 1/2 and combine like terms. We end up with 3/2 plus 2 cosine 2x plus 1/2 cosine of 4x. So the antiderivative of 3/2 is 3/2 x. The antiderivative of cosine is sine, so let's just check and see, does sine of 2x work? Sine of 2x's derivative is cosine of 2x times 2, so that checks out. Plus 1/2 sine of 4x times 1/4 plus c, or 1/4 3/2 x plus sine of 2x plus 1/8 sine of 4x plus c. So the trickiest thing with those is the step where you apply the half angle identity again. And what you do when you do that is this gets multiplied by 2. So had that been cosine of 3x or 5x, then this would be 6x or 10x. In this next example, because the power on the secant is even, what we can do is save a secant squared. So we'll have secant squared theta times secant squared theta d theta, with kind of an end goal of letting u equal tangent of theta. Because if we do that, then du will be secant squared theta. But first we have to change those secant squared thetas into tangent squared thetas. And remember that secant squared theta is equal to tangent squared of theta plus 1. So we have the integral of tangent squared theta plus 1 over root tan theta times secant squared of theta d theta. And now if we make our substitution, this gives us the integral of u squared plus 1 over root u du, or dividing both terms by root u and exponents subtract, we end up with u to the 3/2 plus u to the -1/2. And now anti-differentiate. The antiderivative of u to the 3/2 will be 2/5 u to the 5/2. The antiderivative of u to the -1/2 will be u to the +1/2 times 2 plus c. And let's just insert what u is. We'll have 2/5 tan x to the 5/2 plus 2 square root of tan x plus c. And just a note, you also could write tangent of x to the 5/2 as the square root of tangent to the 5th x. So that's another way to express tan x to the 5/2 power. Sometimes more than one substitution will work. In this next example, we will do this two ways. In the first way, we're going to let u equal tangent x. In the second part, we're going to let u equal secant x. And the answers are going to look different, but they're actually equivalent. So if we let u equal tan x, then du is going to be secant squared x. So what we do is we take off two of those secants and save them. So that gives us the integral of tan to the 5th x secant to the 4th x secant squared x dx, or tan to the 5th x. Notice that secant to the 4th x is secant squared x squared, so that is tangent squared x plus 1 squared times secant squared x dx. And now if we do our u substitution, we have the integral of u to the 5th, u squared plus 1, the quantity squared, du, or u to the 5th multiplied by u to the 4th plus 2u squared plus 1 du, which is the integral of u to the 9th plus 2u to the 7th plus u to the 5th du. And now we anti-differentiate. We end up with 1/10 tangent to the 10th x plus 2/8 or 1/4 tangent to the 8th x, and then lastly plus 1/6 tangent to the 6th x plus c. To me, that's the more obvious substitution, but there is another way. You can actually also u sub for secant, and let's look and see how that works and how it's a little bit different, but the answer is actually. So if we let u equal secant, du is secant x tan x. So I have to save both a secant and a tan. So this becomes the integral of tangent to the 4th x, secant to the 5th x, times tan x secant x dx. So this part's saved to be my du. And then notice that tangent squared is equal to secant squared minus 1. So tangent to the 4th x is equal to secant squared x minus 1, the quantity squared, times secant to the 5th x times secant x tan x dx. And now we make our substitution. So we have u squared minus 1, the quantity squared, times u to the 5th du, which when we expand gives us u to the 4th minus 2u squared plus 1 times u to the 5th du. And distribute, we have the integral of u to the 9th minus 2u to the 7th plus u to the 5th du. And now anti-differentiate, and we have 1/10 secant to the 10th x minus 1/4 secant to the 8th x plus 1/6 secant to the 6th x plus c. Now, proving those two answers are equivalent would just be very, very tedious. You're going to have to use the Pythagorean identities to do so. So it's not very much fun, but both of those methods are legitimate methods, and you can use either one. So sometimes more than one method works. Occasionally, it's a good idea to change trig functions into sines and cosines, and I would say if you're stumped, that's a good place to start. With cotangent and sine, there's no obvious derivative u substitution that will work, so I'm going to change cotangent into cosine over sine. So this becomes the integral of cosine to the 5th x over sine to the 5th x times sine to the 4th x dx, which simplifies to cosine to the 5th x over sine of x dx. Now because that sine's in the bottom, it can't be part of my du. So say if I were to try to let u equal cosine. So what you're probably going to be forced to do here is to let u equal sine of x. And then du will equal cosine x dx. So we save one of those cosines. So we'll write this as cosine to the 4th x over sine x multiplied by cosine x dx, and then use the Pythagorean identities to change that cosine to the 4th x into 1 minus sine squared x, quantity squared. So don't forget about the times cosine of x dx. Now make your substitutions, and we have 1 minus u squared, the quantity squared, over u du. And if we expand the numerator, we end up with 1 minus 2u squared plus u to the 4th all over u. And then divide each term by u, which gives us 1 over u minus 2u plus u to the 3rd du. And now we anti-differentiate. Remember, the antiderivative of 1 over u is ln, absolute value of u. The antiderivative of 2u will be u squared plus 1/4 u to the 4th plus c, and then we'll just insert our u. We have ln absolute value of sine of x minus sine squared x plus 1/4 sine to the 4th x plus c. In this next example, we have the integral of 2 plus sine x all over cosine x. So let's start by making this into a sum of two integrals. So we'll have the integral of 2 over cosine x plus sine x over cosine x dx. And then 2 over cosine is the same thing as 2 secant of x plus the integral of sine over cosine is tangent. And the formulas for these are the integral of secant is ln, absolute value of secant x plus tan x, plus antiderivative of tangent is ln, absolute value of secant x plus c. Or the antiderivative of tangent is also equivalent to secant x plus tan x. Negative ln of cosine x, you also could have said minus ln absolute value cosine x plus c. The reason that is true is this, negative ln absolute value of cosine x. The power, this is a power of -1, this becomes ln of cosine x to the negative first, which is ln of 1 over cosine of x, which is ln of secant x. So either formula, this or this, both are correct. For this example, we are going to use the Pythagorean identity that involves cosecant and cotangent. And what you have to remember is that if you let your u equal cotangent x, du is negative cosecant squared x dx. So since we have cosecant of x to the 4th, we're going to save 2 of those to use for the du. So we can write this as cosecant squared x times cotangent to the 4th x times cosecant squared x dx. Now our Pythagorean identities say that cosecant squared x is equal to 1 plus cotangent squared x, so 1 plus cotangent squared x times cotangent to the 4th x times cosecant squared x dx. And now we make our u substitutions and we have negative the integral 1 plus u squared times u to the 4th du, or negative the integral of u to the 4th plus u to the 6th du, which will be negative 1/5. Put back in what u is cotangent. Cotangent to the 5th x minus 1/7 because that negative distributes. Cotangent to the 7th x plus c. Suppose we want to evaluate the integral of cotangent cubed x. So my first instinct here is to try to use some kind of Pythagorean identity to simplify this somewhere, make it something we can actually handle. So cotangent cubed x is cotangent squared x times cotangent of x. And cotangent squared of x is equal to cosecant squared x minus 1 times cotangent of x dx. Now let's distribute that cotangent of x and break this into two integrals. So you have the integral of cosecant squared x times cotangent of x dx minus the integral of cotangent of x dx. So with this first integral, if we let u equal cotangent, du is equal to negative cosecant squared x dx. So that gives us negative the integral of u du. Not so bad. Now the next one, notice that cotangent is the same thing as cosine x over sine x, which we can also use substitution to evaluate. If we let, we'll say, w equal sine of x, then dw is equal to cosine of x dx, and we have minus the integral of 1 over w dw. Now Now the antiderivative of negative u will be negative 1/2 u squared, which will be negative 1/2 cotangent squared x, minus the antiderivative of 1 over w will be negative ln absolute value of w, and w is equal to sine, plus c. Now to evaluate sine of 5x times sine of 2x, we are going to use the sum difference formulas that were given on your previous set of notes. So if you have sine of a times sine of b, this will equal the integral of 1/2 times cosine of a minus b, so cosine of 5x minus 2x, minus cosine of 5x plus 2x. So that gives us 1/2 times the integral of cosine of 3x minus cosine of 7x. And now we can evaluate this using simple u substitutions in our head. So 1/2, the antiderivative of cosine is sine, so we'll have sine of 3x multiplied by 1/3 minus sine of 7x multiplied by 1/7 plus c. And you can choose to or not to distribute that 1/2. If you do, you end up with 1/6 sine of 3x minus 1/14 sine of 7x plus c. Now in this example, we're going to use a combination of, we're going to do 2 substitutions in a row. So first of all, I'm going to substitute, so I just have secant and tangent of a single thing like u or w. So my first substitution, I'm going to just use w. We're going to let w equal x squared, then dw is 2x dx, or 1/2 dw can substitute for x dx. This means we now have the integral of 1/2, so 1/2 the integral secant squared of w tangent to the 4th of w dw. And now we substitute again, and because the derivative of tangent is secant squared, I will let u equal tangent of w. Du will be equal to secant squared of w dw. Now that gives us 1/2 times the integral of u to the 4th du. Now we antidifferentiate u to the 4th, and we end up with 1/5 u to the 5th, so we have 1/2 times 1/5 u to the 5th plus c, and we substitute everything back in. We have 1/10 tangent to the 5th of w plus c, and we sub back in what w is x squared. We end up with 1/10 tangent to the 5th of x squared plus c.